Okay, how's that mic now? Is that a little bit better? Is that okay, guys? So just tell me if that mic is better. Okay, so today I want to talk about the transport layer. Now I apologise I haven't uploaded my videos, it takes a lot of time to do them and I'm a little bit backed up with other courses as well, so I will upload them as soon as I get a moment. But today I want to go through some of the most important concepts, particularly the concepts around the third question I ask in the exam, which relates to the transport layer. Some of the really fundamental ideas of the transport layer. So particularly the idea of reliable data transfer. So I want to go through this thing called a finite state machine diagram, which allows us to really go through the sequence of events that happens when we do reliable data transfer. So I'll explain what that means in a moment. So maybe I'll actually start off this discussion, I better start recording actually, maybe I'll start off this discussion with a hypothetical situation that I want you to think about, and you can throw out your answers or what you think would be good solutions before I start putting things down on the board. Okay, so okay, am I getting good mic signal? Yeah, Sinead says good mic signal. I've got only 14 people in the room. That's crazy. Okay, I'm going to start recording now. So hopefully, yeah, so welcome to today's lectures. Today I'm going to talk about some of the concepts behind reliable data transfer. So this is the first time you've heard me talk about the transport layer, the next layer in the network stack. So I want to start off with a kind of a hypothetical situation, and anyone who's out there listening, all 14 of you, oh, I've got 41 now, anyone who's listening can maybe throw out some ideas. So I want to give you a sort of a simple hypothetical situation. So imagine you are, I'm going to give you a crazy situation here, but imagine you're in a movie and the movie is about, or you're writing a script for a movie. It's a new Jared Butler classic situation where Jared Butler has to save the President of the United States or something like that. Now Jared Butler has discovered that there's some terrorists, okay? So these terrorists have taken over, maybe they've planted a bomb under the White House or something like that. Now, we'll say you are partners with Jared Butler. So Jared Butler is down, say, let's say this is the White House here. I can't really draw very well. Let's say this is the White House here. And we'll imagine that under the ground, down here, deep under the ground, these terrorists have dug a tunnel down here and they've planted a big bomb here. Big nuclear bomb down here inside this tunnel. And we'll imagine that, say, Jared Butler is down here. We'll put Jared down here, action man. And he's about to, he's trying to put in the PIN number. So he's found the bomb. He has to put in a PIN number to disable the bomb. Now we'll say up here, this is you up here. And you've managed to find one of these terrorists and get the information out of them. So you've got the PIN number. You have the PIN number over here. Now we'll imagine you're on the phone, you've got a dodgy phone, and you need to relay the PIN number to Jared Butler down here. So you want to say, 5, 3, 2, whatever, to Jared down here, and he's going to type it in. Now, if you get one of these numbers wrong, if you give him one of the numbers wrong down here, he's going to put in the wrong PIN number, the bomb's going to go off, it's going to kill loads of people, including the President of the United States. So what are you going to do? This is particularly difficult because the phone line is really, really bad. Sometimes it garbles things up a little bit, so you kind of hear, you're not sure what was just said, and other times it drops completely, so you're not even sure if anything was said at all. So we can garble messages and we can lose messages on this phone line. So how are you here and Jared Butler going to communicate? You have to give him this set of numbers to disable the bomb. And if you get one wrong, if he puts one wrong, the whole thing blows up. And you're on a time. Let's say you've only got a limited time here, so you're under pressure. So what is your solution? How are you going to get these numbers to Jared Butler down here to save the day? And your channel, your phone, is dodgy. So it's going to drop. It's going to drop every now and then, and it's going to garble things every now and then. How are you going to deal with that situation? So anybody want to throw out some solutions? Just shout out now on YouTube here, and I'll see what your solutions look like. Okay, so some people are saying TCP, to use TCP. Forget about TCP for a minute. I want you to just think about, you're on the phone, you can talk to Jared, but sometimes the phone goes dead, sometimes it garbles things so you can't really hear it properly. So that's your network, if you like, that's your communication channel. How do you communicate your message? I want you to forget about TCP. This is really just to try and get you to think about the principles of TCP, which we will of course talk about later. Other messages are coming in. I see some people are saying the recording is low. Okay, so bear in mind I am recording this. I am recording this conversation or this video, so you can watch it back if for some reason the video is low quality. Okay, so what are you going to do? So anybody want to throw out some ideas? You could text him. Okay, Stephen, that's not an option. No text in this situation. Okay, well imagine they're walkie-talkies if you like. You're limited to walkie-talkies and the line is really bad. So what are you going to do? No text message, no data, none of that. Let's see, have him respond to see if he heard you. Okay, the first good suggestion is coming from, I googled Bing, okay, I don't know what your name is, but yeah, the suggestion was have him acknowledge, and I'm going to use the word acknowledge, it wasn't quite used there, but have him acknowledge every time something is sent. Okay, that's not a bad suggestion, but let's have a think about it, okay? So let's say you put in, let's say you shout out 5. So you shout out 5 into your walkie-talkie. And then Jared Butler over here hears something, right? So he hears, what does he hear? He might hear 4. Okay, so he might have heard 4. It might have sounded like 4 because the line went a little bit bad. So what's going to happen now? He's going to put in 4 and boom. Now you said repeat everything back. Could we overcome this problem here? So let's imagine he doesn't hear anything. That's okay. So you might then repeat 5 because you haven't heard a reply. So that would work. Let's say he hears 4 and he responds back 4, and you say, no, I said 5. So in that case, you've worked. Your solution has worked well. You can now say, no, it was 5, and you can correct the problem, and so he won't put in 4. But what if, and of course, if it dropped completely and you heard nothing, you'd wait for some period of time, right? You'd have a timeout value. You'd wait for maybe 5 seconds, you hear nothing, so you repeat yourself. You say, I said 5, right? And then, of course, he might hear it the second time, and he'd repeat it back, and everything's back working again. But let's just explore that a little bit more and we'll see where it can go wrong. Now I said the line can drop packets completely or it can garble them up so he hears the wrong thing, or he thinks he hears the wrong thing. So how do we deal with that situation? So let's say you say 5 and he hears 5. Great, and he says back to you 5. But now let's imagine as he said 5 here back to you, it was dropped. So it never got back up to you. So you never hear 5. So you say, what do you say? You say 5 again. Right? So you say 5 again because you didn't hear his acknowledgement. So now he hears 5 and he puts in a second 5. Boom! The bomb goes off. So let's go through that again. So why did that fail? Why did that fail? So you said 5. You said 5 over here. Then he hears 5. And he says 5 back. Then you hear 5. No. So that would be working well, but what happens if the following sequence happens? So let's say this one never gets back. He says 5, but it never reaches your ears because the line goes dead. So let's get rid of this here now. So you're up here waiting, you've said 5 and nothing's happened. You haven't heard anything back, so what do? Naturally you repeat yourself after a while and you say 5. Of course he hears 5 again down here and he replies 5. And this time maybe you do hear 5 coming back. So what's happened here, he's after entering in 5 twice. No fault of yours, you did everything you should have done, you waited, but because this acknowledgement was lost, everything went down. So anybody else have any more suggestions? How do we overcome this problem? Have him respond to see if he heard you, yeah. Can I shout down the tunnel? Absolutely not. Giving pairs of numbers the place in the sequence and the value to overcome the mix in the number. Bingo from Myween. Well done. Yeah, so Myween's idea was to start putting sequence numbers on the messages. And that's exactly what TCP does. So in that case, what you would have done, you would have said, so you would have shouted out 5, but you would have put a number on it. You would have said, this is my first number, it's 5. 1, 5, say. Sequence number 1, value 5. Over here, he would have heard, Jared Butler down here would have heard 1, 5. And presumably he would have replied then with 1, 5. Or just 1. Yeah, presumably he would have just replied with 1, 5. So then you would have got that back, and if you got back an incorrect, let's just say that was lost. This time coming back, same as before, you're going to wait for your timeout value. You're going to wait for 5 seconds or 10 seconds, and you're going to repeat yourself. You're going to say, I said sequence number 1 is value 5. Number 1 is 5. And then he'll hear that down here again, 1, 5, and he'll realize, hey, I already entered number 1, this must be a repeat. So he's not going to do it again. He's not going to enter it in a second time. And so you've saved the day. If you follow this protocol, you'd have saved the day. Now, one way to do this is to use sequence numbers. So let's say you have to put in 8 numbers down here. Let's say you have to put in 8 numbers. Well, imagine the number is 872687728. Okay, well imagine it's something like that. And you're going to give sequence numbers. You're going to say, okay, this is number 1, 0, 1, 2, 3, 4, 5, 6, 7. These are the sequence numbers of my message. And if you do that, if you keep saying, look, number 0 is 8, number 1 is 7, number 2 is, and so on, and follow the protocol we just went through, everything will work out fine. I suppose originally, this is exactly what TCP does. TCP will give a unique sequence number to each element in the sequence, so that you can always send an acknowledgement for each one, and uniquely identify it. So if there's any need to resend, you'll always be able to identify it. So that's exactly what TCP does. Now, in the simplest possible case, and in the way I've done it in the lectures, I don't know if you've been reading the notes are up, even though I haven't put up the videos yet. The simplest way to do this, as you'll see in the notes, is to start off with just 2 sequence numbers, 0 and 1. And that's all you really need, as long as you're willing to wait. So what you do is, instead of putting in all these different sequence numbers building up, you just put in 0 and 1, 0 and 1, 0 and 1. And let's just see if that works out okay for Jared Butler down here and yourself. So we've got 0, 0, 1, 0, 1, 0, 1. Now, so you're going to say 0, 8, we'll say. This is your very first digit. You're going to shout out 0, 8. And he's going to hear that. Hopefully down here he'll hear 0, 8. Now, just make sure you can still hear me. Checking with your messages down here. Thanks, Ryan. Is there an option to just move the president? Well, we'll see if that option exists very soon, won't we? How's he supposed to know the formatting in this case? You need to establish this before you went down the tunnel. Yeah, I mean, exactly. That's a good point there from Aram. So, yeah, you need to agree. Of course, you would have a need to agree the protocol before you went down the tunnel, because you couldn't communicate him afterwards. So communicate with him afterwards. So of course, any protocol that exists in a network for communicating from one endpoint to another must be agreed by the 2 endpoints before the communication begins. in order to change it, it's difficult. You can't change a protocol while it's in use. It's not possible. So you need to stop everything, change the protocol, get both endpoints to agree, and move on. So in this case, both you and Jared Butler would have had to have had this agreement before he went anywhere near the tunnel. So the protocol must exist before the communication session begins. Any other questions coming in before I launch into the 0-1 idea? Continuously shout sequence recurring. Yeah, I mean that's what I mean by putting in those sequence numbers. I think that's what you mean, Stephen. Giving pairs of numbers. Have him respond. Yeah. Okay. So these are all good ideas. So instead of giving all unique sequence numbers like TCP does, I'm going to go back to some of the original ideas that were used in networks. The smallest numbers we can use here are 0 and 1, and just keep repeating that sequence, and then we just give the values as well with each of these unique, or they're not exactly unique, each of these repeating numbers. So we'll say 8 is the first digit, 08 is the first thing that's communicated here. Jared Butler's, here's 08. So he answers back, he replies, he acknowledges 08, and hopefully you hear that up here. Now as soon as you get the acknowledgement, as soon as you hear 08 coming back, then you can use 1. So as soon as you know that the 0 message was heard, the first message was heard, then you can start to use your new sequence number 1. So then you say 1, 1, 7. And so so Jared Butler down here will hear 1, 7, and he'll know this one is new. Because it's 1 and the previous one was 0, he will always know that this is a new number because it's different to the last one. So that's how 0 and 1 are enough to do everything. So we only actually need, in the minimal case, we only need 0 and a 1 as sequence numbers. And as long as we're willing to wait, as long as we're willing to wait, sorry, that should be 1. As long as we're willing to wait for an acknowledgement with that sequence number in it, then 0 and 1 is all we need. So we say 0, he hears 0, he replies the 0, then we say 1, he replies the 1, then we say 0 again, this time we're using number 2. Sorry, we hear 1, 7 coming back. Then we say 0, 2, so you'll hear 0, 2. And again, it's okay because the last time sequence number 1 was used. So it's okay to use 0 the next time. Hopefully you get that idea. So as long as we're willing to wait, and this is known as stop and wait. As long as we're willing to wait, 0 and 1 is enough. So let's explore what could have happened here if things had gone wrong. Let's imagine we went for 08 and he heard it down here and he replies 08, but we'll imagine that's lost. We'll imagine we never hear that one coming back. So what do? We're going to wait for some period of time like you would in a normal conversation and before you repeat yourself. So if you don't get an acknowledgement or an answer, you're going to repeat yourself, and in this case you're going to repeat 08 again. Now, of course, he's already received 08 and he's already replied. The reply was lost. But because 08 comes in a second time here, he knows it's a repeat of the same earlier message. He's not going to type in 8 again and blow up the White House. So he's going to reply a second time at 08, and hopefully that'll get things back on track. Hopefully the reply will come in 08 and he can move on to 17. So as long as we have a 0 and a 1, that's enough. And as long as we're willing to stop and wait before we send the next message, and wait for an acknowledgement before we send the next message. So that's kind of the basic idea. Let's go through the main points there. 0 and 1 sequence numbers are enough for reliable data transfer. That's what I mean by RDT. I use that abbreviation quite a lot in the notes. So 0 and 1 sequence numbers are enough. Of course you can use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 as much as you want, but 0 and 1 are enough if you're willing to have stop and wait. If you stop and wait. So stop and wait means that you can use 0 and 1. If you don't use stop and wait, if you're willing to use all the sequence numbers up here, if you're willing to go 0, 1, 2, 3, 4, 5, 6, 7, and so on, then you don't need to stop at all. You can throw them all out at the same time. You could say, Jared, 0 is 8, 1 is 7, 2 is 2, 3 is 6, 4 is 8, and so on. You could just throw them all out, and he can write them all down, and if he misses one, or if one doesn't look, he can repeat them all back to you. So the more sequence numbers you use, the more you can throw into, the more values or messages you can throw into the channel without waiting for an acknowledgement. But if you're using just 0 and 1 for your sequence numbers, then you must wait for an acknowledgement every single time you send a message. But it's the simplest case, so it's the one that we're going to explore in more detail in the notes. And right now. Okay, let me just check the, the other big thing there was, there's a few other things to come in here. I'm just going to make a note of a few big things here. So number 1, 0 and 1 are enough sequence numbers to use with our messages. Number 2, so long as we're willing to stop and wait every time we send something, we stop and we wait for an acknowledgement. Number 3, timeouts. We need a timeout. We need this. Is needed if the channel will drop packets. What about the garbling messages? What about that, where we flip bits, if you like, and we don't hear things correctly? Okay, the message has not been lost or dropped, but it's been misinterpreted. So there's errors in the message. How do we handle errors? So we can handle a dropped packet with a timeout. We just don't get our acknowledgement back for a while, so we send a repeat. That's our timeout case. But what about errors in the message? Now in this case with Jared Butler, we had him repeat back the same thing that he heard. But I mean, if you were to explore that idea a little bit more, if you were to say, look, well, he sends an 8 here, and this maybe he hears a 6, maybe he actually hears a 6, and maybe he sends back a 6, but you hear an 8. So that might not have worked out well, but anyway, it's a way of dealing with it. It's unlikely that would happen, right? But so what we do in computer networks is we use some kind of a way of error checking. So we need error checking. We need some way of error checking the message. Error checking is needed with errors, with channel errors. Okay, so there's two different things there. So the channel can drop packets. That's one problem. We're going to use timeout and resend to deal with that. And by timeout, I mean we're going to wait for an acknowledgement. If it doesn't come within a certain time, we'll resend. The second thing is that if there's errors in the channel, how do we deal with it? Well, we need some way to check for errors, error checking of the packets. And we're going to use something called checksum. We're going to explore that a little bit. Checksum. So these are really the main ideas, and if you kind of get these ideas, then question 3 in the exam is really easy. It's the least answered question by a mile because people get scared of it. It's the only one you really have to think for yourself if you want to do it. But it's also the shortest one. You fly it. If you know what you're doing and you kind of get these ideas, you can really fly through it pretty quickly. So I'm going to go through an example of it now. I'm going to take 1 or 2 questions. If you're using 0 and 1, what happens if he doesn't hear 2 in a row? That's a good point there. Yeah, that's a slight failing there in the idea. You're right. I mean, if he wasn't to hear 2 in a row, you might think that's a problem. But remember, you're waiting for you're waiting for an acknowledgement. So, well, the only way that could really be a problem. So the question was, what happens if you do 0 and 1, but then he skips 2 messages and he goes back onto the 0 and 1 when you're repeating them. And the answer is that can't happen because you're stopping and waiting every time there's a single 0 or a single 1. So you can't have a case where a 0 and 1 go in erroneously. So when you send a 0, you have to wait until you get back an acknowledgement for 0 before you can send the 1. If that makes sense. So it could never happen that there would be both a 0 and a 1 unacknowledged at the same time. So it could never happen that he would receive a 0 and a 1 in sequence that were both erroneous. Okay, so I hope that answers your question there. And I think that was Ryan. Ryan, I think it's a great question, but I think you'll see, particularly as I move on to the finite state machine diagrams, you'll see that can never happen. So I'm going to take this idea now. Before I move on to any exam questions, let me see how am I doing for time. Yeah, I'm okay. So before I move on to any exam questions, I'm going to take all of these ideas that we've just done, and I'm going to show you how they work in a finite state machine diagram. And hopefully, having come from this really simple, practical movie example, and moving into the finite state machine diagram description, you'll really be able to understand what's going on and use the ideas. Okay, so I'm going to rub this out, so give me a moment. And if you're just sitting at home right now and you have the notes in front of you, you can look at your notes for reliable data transfer 3, I think, is the most advanced one, but we're actually already able to do 3 now, just after this discussion. In the notes, I build it up very slowly using the ideas of the finite state machine diagram. I'm just going to go straight at it here, and I think it's almost better just to learn by example, I think, sometimes. So finite state machine diagrams are particularly useful for understanding a sequence of events and how they will and how it all works together. So if you were to try and very formally describe what I just went through with Jared Butler here, how would you do it? You'd probably write out all these rules and instructions, and that's exactly what finite state machine diagram does. It allows you to see all the rules in a really simple way. If you like, you can graph it. You can kind of visualize the rules a little better than writing them all down in a list. Okay, so let's go through it again and just check your questions coming in here. Doesn't the repeat already have an inherent error check? From Stephen, yeah, the repeat will have to have an error check as well. That's a good point. So we're going to need error checks. We're going to need error checks on both the messages going to Jared Butler, and we're going to need error checks on the acknowledgements that comes back, so that we know that it is an acknowledgement or a negative acknowledgement, or a NAC as they call it. Okay, so let's go through it. So, any other questions? Okay, I think everyone's okay. So how's the connection? Can I get any feedback on the connection? It seems to be getting better here. I see YouTube are happy enough. What's the delay like? Kevin has just asked, I'm not confident that Jared Butler could execute this plan. Yeah. Okay, so let's go through it. So, right. So this is we're going to need a finite state machine diagram at both the sending side and the receiving side. Okay, so Jared Butler needs a plan, and you need a plan. So we're going to do that plan using your plan over here with one finite state machine diagram, and we'll have a plan over here for Jared Butler with a different finite state machine diagram. So you both need your plans. Both plans will be described with this diagram, rather than writing out big long rules. Let's go through it again. So what is the plan here? We're going to use the plan. Okay, so the basic ideas. Okay, so basic plan. Basic plan is number one, we're going to use timeouts. Timeout, resend. So this will deal with dropped packets. And we're going to need a checksum. We're going to need some way of checking that there's an error in the message. We're going to use something called a checksum. And what a checksum does, so we'll use checksum. So what a checksum does is it does a calculation. It does a little bit of maths on the message. So it uses the bits in the message. It does a little bit of maths with the bits, and it puts the answer inside the message. And then the receiver, when they get the message, they do the exact same little bit of maths on the ones and zeros, and they look to see if their answer matches the answer that you included. And if they match, then you're okay. Then there's no bits that are incorrect. There's no flipped bits. So that's what checksum is in a nutshell. So deals with flipped bits. Bits or errors in the channel. So for Jared Butler, this was a case where you couldn't quite hear him. You thought you heard something, but you weren't sure. And then this former one deals with an entire, a dropped packet or a silence. In the case of the Jared Butler example. Okay, so that's the plan. And we're going to use just two sequence numbers. Choose two sequence numbers, 0 and 1, and stop and wait. Okay, so that's everything. So this is going to deal with, so stop and wait is where we send our packet number 0, and then we wait until we get back an acknowledgement for that. And we won't send anything else until we get back an acknowledgement for packet number 0. And when we do get that acknowledgement, then we send packet number 1. And then once we get the reply for that, we send packet number 0 again, and so on, and so on, and so on. So let's go through it. So these are the rules. This is the plan. Let's draw your finite state machine diagram first over here. See if there's any messages coming in. Long enough delay and low frames per second, but connection strong. Audio is coming quite through. Okay, that's good. Good to know. Remember, I am recording, so this is recording as well, so there will be a higher quality stream or video if you wanted. Anyway, so let's go over here. So we're going to have a first state. So we always have these things called states in a finite state machine diagram. So this state is just wait for packet 0. Okay, so that's this state, and nobody's in that state yet. So when a message comes down from your application layer, okay, so let's say it's WhatsApp or whatever that you're dealing with, or whatever the application is that you're trying to reliably transfer. Maybe it's an image from WhatsApp or something. So WhatsApp knocks on the socket. Remember that socket? And then this is right behind the socket. So let's say this message comes in, this part of an image comes in from WhatsApp on the other side of the socket door. Okay, so this is the first state we're going to enter into. So that's what the dashed arrow means. This is our initial state. We're waiting for that first packet to send. So suddenly WhatsApp knocks on the door, gives us the data. Okay, so what do? Okay, so I have particular notation in the notes. I'm just trying to remember it now. What is the notation? I want to make sure I use the same notation because I don't want to confuse you. So give me one moment.